Let's finish off chapter 1. A few notes before we get started here. So the topics today are decomposition of ozone in the atmosphere. So we've talked about production of ozone in the atmosphere already. How does oxygen O2 form O3? So if you might want to go back and just look at that briefly. So today we're talking about how ozone is depleted, which is often the phrase that's used, or destroyed in the atmosphere by either natural causes or, well, unnatural causes, man-made, anthropogenic. And that's what we're talking about here. So let's finish this off. Also, I want to give you a heads up. I'm not covering this in the level of detail in the book. The book goes through several mechanisms for how ozone is destroyed. I'm simply going to give you an overview of those mechanisms. And when I say mechanism, I mean kinetic mechanisms where you have multiple steps adding up into an overall step. We've seen one example of that already. And then also how the production of ozone links with the destruction of ozone into a cycle. So it's always being produced, it's always being destroyed, and we can think about it not as a series of reactions, but rather a cycle of reactions, which is a different mindset change if your background is specifically chemistry. Okay, let's finish it off. Okay, so we have one last slide to do here. It's, what slide is that? Slide 8 or something like that. Yeah, and the graphic that's on there is worth mentioning. I don't think this graphic is in your book. If it is, it's in some other chapter. And I guess I can hold this up here, but you probably have this in front of you. Yeah, okay, that's the slide I'm talking about. In 1987, incidentally, which is the year I graduated from high school, there was something put into place called the Montreal Protocol. What this was a way of reducing the number of gases that were released into the atmosphere that contributed to the destruction of the ozone layer, which was a serious concern because of the additional ultraviolet light that would come through the stratosphere, not the troposphere, the stratosphere, and then cause health problems on the planet. And some of those health problems I put as homework that you'll go through and discuss. I'm not doing that qualitative stuff during these lessons. So that was an example of a really effective international treaty. It's called a protocol, I'm not really sure the reason why, that reduced a lot of chemicals that were being released. The ones you might have heard of are called CFCs, chlorofluorocarbons. And there's a whole class of molecules there in the legend. Now this graph shows you, well, how did the Montreal Protocol work? It worked really well. It reduced a lot of the chemicals that were put into the atmosphere that caused ozone destruction. And there was a projection there with and without the Montreal Protocol. That's an example of a very, very successful international treaty. And you'll probably end up reading more about that as a homework assignment or a take-home exam. But if you'd like to look up the history of that Montreal Protocol, what it was designed to do, please do so, but I'm not going to do that here. Okay, let's talk about the chemistry. So we are under letter D. I guess I can do that. I'm not sure I'm going to fit this all on one board, but I might try actually. So D, destruction of ozone. You probably can get that better from the slide. Now this is divided into two sections. Well, natural, okay, which are also called non-catalytic. Did I spell that right? Yeah, okay. So remember what a catalyst is. So that's something if you want to go and look in the book under the kinetic sections. A catalyst is something, well, a couple things about it. A catalyst accelerates the rate of a chemical reaction and then it regenerates itself. So a catalysis is used, but then it's regenerated. So you never see it in the overall chemical equation, but you see it in the individual steps in the mechanism. The other thing that a catalyst does, it reduces that thermodynamic barrier called activation energy. And I think I was going to put this a little bit later, but I think I'm just going to do it now. So this is again the kinetics chapter, and this is a theoretical graph, by the way. So if you graph potential energy, so PE, potential energy on the y-axis, versus what's called the reaction, RxN is a common abbreviation, coordinate. Now, coordinate is what that's called. Now, this is conceptual. So what happens is your reactants start off at a certain energy potential. And the products, well, it depends. If it's an endothermic reaction, the products end up here. If it's an exothermic reaction, which most of them are, they end up down here. So these are reactants and products. I'm just doing this in a very generic sense. This would be exothermic. I think I have a homework problem where you draw something like this. Okay. And then to make the reaction occur, or a step in a reaction occur, there's an energy barrier that has to be overcome. And the amount of energy that has to be overcome is called the activation energy. Those two green boxes, box 1-1, box 1-2, go more in depth into activation energy and also using an equation called the Arrhenius equation, which I'm not intending to spend time on during these lessons, but I leave that kind of as a self-study for you to do with one of the homework problems. The point for this particular part is that a catalyst lowers the activation energy. It makes it easier, if you will, thermodynamically easier, less energetic to occur, which a effect of that is it makes the reaction faster. Okay. So that's really just vocabulary to understand this. So the first mechanism for destruction of ozone is non-catalytic, which I suppose we can call natural mechanisms. And there's a couple of these. So we're destroying ozone, so it probably makes sense that we're going to take ozone gas. I'm going to stop writing G, gas, because why? We know it's a gas, so it just clutters things. So this is not a catalyst. So ultraviolet light, more specifically ultraviolet C and B, as we know the most energetic forms of ultraviolet light, more specifically wavelengths less than 320 nanometers. That's pretty high energy. So what happens is ozone gets hit with ultraviolet light of a specific wavelength, and you end up getting, well, okay, introducing this symbol. This is this asterisk is often used in chemistry. What does that mean? You may remember this. This means an electron in an excited state. You might remember that electrons, when they're in their lowest energy state, that's called the ground state. We're not doing things like 1s2, 2s2 orbitals. We could, but it doesn't really add a whole lot. It does in another section in the book. And then when electrons are not in their lowest state, they're in an excited state. What excites them? Well, an input of energy. It could also be a flame or something like that that might cause an excited state. But in this case, it's the ultraviolet light. If you want to write here, the lowest energy is called the ground state. I don't think I need to write that here. So that is, so ozone is split into two excited state species, diatomic oxygen and atomic oxygen. So diatomic and atomic, monatomic if you will. And that's the first step. And then the second step is that another ozone, not the same one, reacts with that atomic oxygen that is produced. And now you get two oxygen atoms. And let me see, I have to look at my notes here. Okay. And that's the non-catalytic mechanism. That's the only one. I had to look at my notes, I was getting confused. There are actually multiple mechanisms for the catalytic one. I got off track there, my apologies. So there's two steps here, and it's pretty straightforward. So What happens naturally, again, this just happens, is ozone is split into two species, and then okay, great. And the only comment I want to make here is this has a pretty high activation energy. In fact, I'm kind of cutting my notes a little bit short here. Fine. So this has a fairly high activation energy barrier to overcome, but I'm more interested in just the chemistry of this. Now, what happens is, we talked before about the production of ozone. This is the destruction of ozone, and then what we do is combine this, and this is called the Chapman cycle. And speaking personally, I don't find these cycle diagrams all that helpful. You have chemical equations that produce ozone, you have chemical equations that destroy ozone, and that's how I think about it. But sometimes people find these cycles really helpful. So here's the way the cycle is written. If it makes sense to you, great. So we start off with oxygen. I think this is the same as the first, yes, this is the same as the first step. So you have UVC and B, and we produce atomic oxygen, okay, and then that reacts with diatomic oxygen to produce ozone, and I think we talked about that before, and I think I made a mistake. I don't think this is UVC and B. I think this is just UVC. You can tell that these diagrams kind of even confuse even me. But then, to go the other way, UV, C, and B can produce this oxygen, okay, and then we get stuck in this cycle, but then ozone goes back that way too, if you add atomic oxygen. Again, I don't find these cycles particularly helpful. In fact, you may have just been confused about what I just did there. So what I would do is read the book, go through the cycle, because it tries to take all of this chemistry and put it into one little graphic. And if it helps you, great. For me, I just kind of prefer to think of them as two separate sets of chemical reactions, and then you just sort of look at them and add them together as necessary. So maybe that was a little bit confusing, but that might be what you need. Okay. And finally, and my little dream of putting this on one board, that wasn't going to happen anyway, is you can go set up the heading, excuse me. Boy, I'm not really doing very well with this one. The second one is catalytic mechanisms from mainly anthropogenic sources. I think that's what the slide has, I hope. Yeah, so go ahead and set up that heading for number 2, and I won't even bother with it. So this is heading number 2, catalytic mechanisms from primarily anthropogenic, human-made, human-induced sources. Okay. While I'm erasing the board, I always like to do a little bit of show and tell. One of the homework problems has you use a NASA website to take a look at ozone levels globally, and also how they're measured using another unit called the Dobson unit, which is assumes that the ozone is like a thin layer. So it's more of a conceptually easy way of measuring ozone as an actual physical layer. But I'll let you. Okay, let's pick up and see if I can clean this up a little bit. So we're down to the last couple. I am giving you an overview here, okay? The book goes through a lot of specific examples of things that are catalysts. I'm going to do it in a very generic sense, so I'm not doing exactly the same way the book does. So what I'm going to do is this, I think the book might do it this way. Let's see if we can fit this close to the board. I'm just going to use the generic placeholder of X as an atomic or molecular catalyst. There are lots of examples of these. All those molecules listed on that graphic for the Montreal Protocol. Those would all be catalysts for ozone. I'm not going to go through every single one of those because we don't need to. I can talk about this in a general sense, show you one example, have you read about more examples, and then write out more examples as part of the homework. That would be busy work to do all of these, but I want to talk about some of the main ones. So what are some examples of X? This also builds our vocabulary. Okay, might as well, so chlorine, if it was a completely neutral of full shell of electrons, we'd have 8 electrons, the octet rule. This only has 7, so this is not stable chlorine. This is what's called a free radical. A free radical is something that has an odd number of electrons. So you have 1 or more, typically it's 1, unpaired electron. These are very reactive species. Sometimes they're reactive in a good way, sometimes they're reactive in a bad way. In this case, they're bad, I guess. So another example would be another halogen, and the book goes through more of the halogens, so you'll see the pattern. Fine, that's a bromine free radical. A very common one that was actually discovered fairly recently. This is an incredibly important, I'm going to put this as an asterisk, I wouldn't want to do that. This is called OH or hydroxyl free radical. A very important one to know. Some other ones that are fairly common is nitrogen oxide. Nitric oxide, free radical, and what does that look like? That looks like this. It's nitrogen double bonded to an oxygen. The oxygen has an octet, the nitrogen does not. And yeah, I have a couple of notes about these two. I wasn't sure I was going to give those, but I think I will. Just some additional context here. All these things have to come from somewhere. So where do they come from? Well, they come from a lot of different places. So these are man-made sources. So where are they coming from? So you may have heard of nitrogen oxides. Those are collectively called NOx, NO subscript X, to indicate there's a variety of these things, like NO, NO2, N2O, collectively called NOx. So that is a fairly common pollutant from the burning of fossil fuels is one place where they come from, especially impure fossil fuels. And okay, so that's one example, and that can actually react with, we're not going through all of this. If there's any atomic oxygen around in an excited state, that will produce 2 of these radicals. Now, N2O is actually a pollutant, has deleterious biological effects on its own, but when it reacts with something like atomic oxygen, it produces something else that can then go off and destroy the ozone, just as an example. An example of how we get hydroxyl radicals. You've probably heard of that molecule, that's methane. So that's the primary component of natural gas. So when that gets into the atmosphere, that actually contributes to climate change quite a bit. This is very good as heat trapping gas, just like carbon dioxide, but this is a much more potent greenhouse gas. So there's multiple effects of these molecules in the environment. In this case, what methane can do when it comes into contact with excited state atomic oxygen, which it will if it gets into the atmosphere because of those reactions I showed you before. Atomic oxygen in an excited state is just a fact of life. Well, Well, that can produce the hydroxyl free radical, this, and CH3, which is called a methyl free radical. If you want to draw out the electron dot structures for these to show why they're free radicals, and so you can see the individual electrons to make the case for yourself, that's fine. You don't really need to do that. And the last example of one that is common are oxygen connected to some halogen. I'm just using chlorine as one example. In this case, the oxygen has the octet, and the halogen, the chlorine in this case, has it. This is called a ClO free radical, or well, I guess you could call it chlorine monoxide free radical. Okay. I think we're down to the last thing. So those are just examples of free radicals. Your book gives you more. What I want to show you is there are two mechanisms that these free radicals react with ozone in order to destroy it. And what does that mean, to destroy it? That means to, maybe that's not a great word, it's almost restoring it back to O3 going to O2. It's the opposite reaction that we did before of producing ozone. Maybe that sounds kind of obvious, but that's what we're doing here. There's two mechanisms, and they're called mechanism 1, great, and mechanism 2. I'm just going to go through the generic placeholder with X, and then I'll show you one example using one of these. So I think I am actually going to need to erase the board again. So mechanism 1, mechanism 2, if you want to set up some headings, I'll do them side by side. You might want to do them top to bottom in your notes. And remember, commit to memory, the hydroxyl free radical. The hydroxyl free radical is enormously important for atmospheric chemistry. Not we're going to see it in this chapter, but the hydroxyl free radical acts as almost a cleanser in the atmosphere to destroy other pollutants, which I think was only discovered about 15 or 20 years ago. So that's a fairly new thing. Okay, so let's just do these. These you can look these up in the book just as easily as I can, and remember when we say mechanism, we mean a series of steps. This is not the best marker. Leading to an overall reaction. Let's just do these side by side. And then I'll do one example for you. I might have just lifted this from the note from the book, but then you'll do some other examples for homework. Okay, mechanism 1 has step 1, step 2, and that'll add up to an overall. And mechanism, so we have 2 steps in mechanism 1, and you add them together and get the overall reaction. Mechanism 2 has 3 steps. Step 1, step 2, step 3, and these add up to an overall reaction. Now, this is just to make sure we understand. Mechanism means individual steps adding up to an overall. Happens to be 2 steps here, 3 steps here, and great. Okay. And so the first one is you have your free radical reacts with ozone, and the first step is that free radical plucks off one of the oxygen atoms. Just bonds it, breaks the bonds, and pulls one of the bonds away, leaving us behind with our starting material from the production of ozone, oxygen. That species, an intermediate species, comes down here, reacts with atomic oxygen, again, that's always present in that Chapman cycle. Maybe the Chapman cycle is helpful for that. All that stuff is present all the time, which is different from thinking about reactants turning into products. Where did this come from? Well, it's always there. And what does this mean? This means, this shows a couple of things. When you add these together, you get O3 plus O forming 2O2. That doesn't look very interesting by itself. But we are reforming oxygen, so we are destroying ozone, if you will, or depleting ozone, maybe that's a better word. And this also illustrates the concept of an intermediate species. The intermediate species is produced, then it's used, so it ends up canceling. It's not really canceling, but does not appear in the overall equation. Also, the free radical catalyst is regenerated. So that's a definition of a catalyst. It's used, but then it's regenerated, and it also does not appear, maybe I shouldn't use X's to mark out X's. It doesn't appear in the overall reaction. But it's really important to understand how those things give us this overall reaction. This is fine. This doesn't tell us why. This is the end result. This is how you get there. The mechanism tells you that. The second mechanism is a little bit more complicated because it's 3 steps. But the first step, guess what, is the same. The free radical reacts with ozone, produces that intermediate species, and our first oxygen atom, our first diatomic oxygen species. This one actually involves 2 different free radicals. So you have another free radical, so X prime, that's just used to mean something other than X. Reacts with ozone. So this is more than one free radical reacting in the same space. Again, it might make more sense to read this in the book than to listen to me. I think it might make more sense. Do both. Okay, well, these 2 steps look pretty remarkably similar, don't they? Because it's one free radical doing this and another free radical doing the exact same reaction. No problem. The last step is you almost have to conclude, and one thing I love about atmospheric chemistry, it tends to be somewhat simple and fairly logical, is those 2 intermediate species, well, they have to react with one another because they're going to have to cancel, and guess what they do? They regenerate the original free radicals and another oxygen. That's a lot simpler than oxidation and reduction chemistry, isn't it? So if you do the overall, this is cancel stuff. So that cancels with that, that cancels with that, that cancels with that, and that cancels with that. So guess what you get? 2O3 going to 3O2, which is exactly the opposite reaction of the production of ozone. So this is the catalytic decomposition of ozone. That's a better word, decomposition. Not depletion or destruction. Decomposition is probably the best word. So you get this going on here. So it's a 3-stepper. I don't think actually these are too difficult to grasp. Basically 1 free radical and 2 free radicals acting in conjunction. And just to give you an example, your book asks you to do this. Show the chemical equations for mechanism 1 with this radical. I'm not even sure I need to do this, but let's do it. So show hydroxyl radical, because that's so common, catalyzed. So this is mechanism 1 or mechanism 2, because it's non-catalyzed. It's the same reactions all the time. The first one I showed you, there's really nothing else to do. So hydroxyl catalyzed O3, I'm going to change my notes. Decomposition. Technically, I guess it is decomposition. It's O3 going to O2, big to small. So that's technically decomposition. Well, we have to know which mechanism. Well, actually, if that's all I say, I guess it could be, well, you know what? It could be mechanism 2. X and X prime would just be the same thing. That seems kind of dumb. Yeah, I guess that wouldn't make any sense. If I gave you just this, hydroxyl radical catalyzed decomposition via mechanism 1. Okay, I think we can make the point. All we're doing is putting in OH where there's an X. I mean, maybe this is insulting your intelligence, I don't know. So let's just do this quick. So step 1, step 2. And if you do it right, the answer is always the same, isn't it? So the answer is that would be O3 plus the atomic oxygen running around, making 2O2. I mean, that's the answer for every mechanism 1, so regardless of what we do. So again, okay, so step 1 is the hydroxyl free radical, just plus O3. Yeah, I feel a little silly doing this. And but because how do you write it? HOO, so that just plucks off. So ooh, sorry, that was horrible. Plus oxygen. I think this is called a peroxy free radical, because peroxide is H2O2, so this is just HO2. I think that's what that's called. If you want to look that up, I think that's a peroxy free radical. Look that up in the book. I'm not going to turn pages now. And then that comes down here. That peroxy HOO free radical reacts with atomic oxygen to do, well, to regenerate the original free radical. Whoops, I wrote that as OH there and HO there. You know what? That doesn't matter. I'm kind of glad I made that mistake in these notes. OH and HO, okay, those are the same. Plus O2. And does it work? Yeah, that'll work. 2 O2s. Yeah, okay. And I believe that is it. So those are the lectures for lessons for chapter 1. I forget how many there are now, 6 or something like that. So make sure you take a look at the homework. There's a few things there that you choose. And if you look at the homework, I'm not asking you to do every single problem. I give you choices of certain sets of problems to do. But make sure you give me the feedback on these lessons. So I'm not sure if you're even listening to this for this reason. But now that we're done with this chapter, you should be good to do all the homework, and then we will move on to chapter 2.